Morning, everyone. Welcome to our tutorial, the natural and artificial dynamics in graph neural networks. I'm Dongqi Fu, the PhD student from the Computer Science Department, University of Illinois at Urbana-Champaign. So this tutorial is co-authored with UIUC PhD student Zhe Xu and UIUC Professor Han Tong and Professor Jingrui He. So all relevant materials for this tutorial will be stored in our GitHub repository. So let's start. This tutorial will last for 3 hours, where we have 30 minutes reserved for the coffee break according to the conference agenda. This tutorial is hybrid. Part 1 and Part 2 will be virtual, and Part 3 and Part 4 will be offline. So first, we will present the introduction part of this tutorial, where we will briefly introduce some background knowledge about graph neural networks, the definition of natural and artificial dynamics, also with the motivations about why we want to give this tutorial about natural and artificial dynamics in graph neural networks. Then we will introduce several interesting works studying the natural dynamics in graph neural networks and mainly focus on their technical details. So after 30 minutes of the coffee break, Zhe will take over the tutorial and continue it about introducing the research works of the artificial dynamics in graph neural networks. Finally, after the introduction about the challenge and future directions for the research opportunity, we would like to answer any questions from our audience in the Q&A session. According to the research, the general formula of graph neural networks can be expressed as follows. In a layer of a certain graph neural network, an aggregate mechanism, or so-called message passing schema, is called to aggregate the information for a node from its neighbors at the previous layer. Then a combine mechanism is used to combine the aggregated information with the node representation at the previous layer to obtain the node representation at the current layer. For example, as shown in the equation, for the neighbor nodes hidden representation at the k-1 layer, we first aggregate them. Aggregate them all and obtain the vector avk. Then we can combine the vector avk with the vector hvk-1 to obtain the node representation hvk at the current layer. The above introduction is a general form of the graph neural networks. For example, a classic graph neural network, GCN, or graph convolutional neural network, can be instanced as follows, where the aggregate is instanced by the mean operation, and the combine is realized by the learnable weights with the ReLU activation function. The original formula of GCN can be expressed in the bottom. The matrix A hat means the normalized adjacency matrix, and matrix A tilde means the original adjacency with the self loop. So graph neural networks have very broad application domains. In the computer vision, graph neural networks can help detect objects by viewing pixels as the node. In the natural language processing, graph neural networks can help classify documents by viewing words as nodes. Also, graph neural networks can help recommend merchandise or discover new drugs. For each application domain, we list the reference of some surveys for your information in the bottom. So after introducing the graph neural networks, so let's then look at what are natural and artificial dynamics in graphs, respectively. So first, as for natural dynamics, which suggests that the input graph has the time evolving components. For example, the topology structures, the node level or edge level features, etc. So moreover, we have the continuous and discrete representation of time. So taking the time evolving structures as an example, in continuous time, the temporal graph can be represented by an initial state with the following events. That is, an event may stand for the added or deleted edge. Well, in the discrete time, the temporal graph can be represented by a sequence of graph snapshots. So each graph snapshot has its own node set and edge set, as shown in the right-hand side picture. Then, after we introduce the natural dynamics, let's look at what are artificial dynamics in graphs. So artificial dynamics means that the end users can change, for example, filter, mask, drop, or augment the existing, or construct the non-existing graph-related elements. For example, those elements can be, but not limited to, graph topology, node or graph attributes, graph neural network gradients, or something else, etc. So after corresponding modifications, the end users aim to obtain the performance upgrade in certain metrics. For example, like decision accuracy, computational efficiency, model explanation ability, and something like that. So to the best of our knowledge, the earliest relevant concept of artificial dynamics in graphs appeared in 2003. So at that time, artificial jump is proposed to adjust the graph topology for page rank, realizing the personal ranking function on structured data. That is, a random surfer or a random walker could follow an originally non-existing but newly added edge to jump to a personally selected node, predefined teleportation probability. Then, what are the relationships between natural and artificial dynamics, you may ask? So intuitively, natural dynamics can be understood as a sequence of observation of graphs based on time. So just like our daily World Wide Web, like Facebook or Twitter. Well, the artificial dynamics means that the end users could deliberately modify the certain components of the input graphs for the different interests. For example, the input graph may have redundant edges, missing features, or etc. Then a spontaneous question is to ask, is that natural and artificial dynamics can be combined, like the natural plus artificial dynamics? The answer is yes. So when the input graph is time evolving and some certain modification is necessary, then natural plus artificial dynamics makes the sense. So which direction is nascent? And we will introduce some related work in the fourth part of our tutorial, that is challenges and future. So after we introduce the definition of natural and artificial dynamics, you may ask why we should care about them in our graph-based research. So first, let's see how natural dynamics contribute to graph neural networks. To be brief, so considering the natural dynamics can help graph machine learning models to capture the temporal correlations among the features. So for example, in the following figure, can we identify that it is running, dancing, or just a static model for the photography? We may not 100% sure about which action it is, or yeah, we're not sure about that 100%. But if we can see the temporal context about that, so given the information, we may see the previous and the future information, so we can know that it may be the running instead of dancing or a static model for the photography. So also considering the natural dynamics can help graph neural network models to accomplish many more applications. In addition to the motion recognition application we just discussed, studying the natural dynamics can help graph neural networks to do the, for example, time series forecasting, pandemic classification, social network analysis, and many, many more. So we also prepare some literatures for your reference in the bottom of this page. Next, let's figure out why we need to pay attention to artificial dynamics in graph-based research. So let's first check out the following toy example of social network anonymization. So for a social network, given the left-hand side connections, an attacker may easily identify your identity since a person connects father, mother, and sister may be highly likely being you. But if we mask the social connection between you and sister, so maybe the attacker could the attacker know the central person is you for social? It may be not, since the teacher may also know both of your parents and make the acquaintance. So, which means that the candidate set for identifying your identity is enlarged by masking a connection in the social network. So also, considering the artificial dynamics can also contribute to other graph neural network applications. For the privacy preserving needs, we can permute the graph neural network model gradients under the differential privacy constraints to generate secure graphs. Also, in certain scenarios like missing features or heterophilic graphs, we need to stack more graph neural network layers. So adding the weights dependency across graph neural network layers can preserve the graph topology property when dealing with the overfitting issue of the deeper graph neural network models. So moreover, when we have a pre-trained large-scale graph neural network, but facing a different distributed target downstream task, we can modify the downstream graphs a little bit to bridge the distribution instead in order to warm up the large foundation models for the downstream tasks, which technique is recently called graph prompting. So also some literatures are listed here for your reference in the bottom of this slide. So natural dynamics and artificial dynamics in graphs is a large topic, so which consists of many different aspects. So here in our today's tutorial for natural dynamics in graph neural networks, we focus on the time-evolving graph structures and node features. For example, as shown in the first picture, the features are evolving along the time dimension. So for the artificial dynamics in graph neural networks, we focus on the augmentation strategy that are designed on graph structures and node features. For example, as shown in the second picture, the features are modified by certain designed strategies. So for the natural dynamics introduction of the graph neural network, we will cover the research works in the following 5 dimensions. So the temporal, so they are the temporal graph neural networks with the convolutional operations, the temporal graph neural networks with recurrent units, the temporal GNNs with the time attention mechanism, the temporal graph neural networks with the time kernel function, and also the temporal graph neural networks with the temporal point process. For the artificial dynamics in the graph neural networks, so we will cover the research works in the following 2 dimensions. So intuitively, the heuristic-based techniques means that the augmentation strategies are non-learnable, but designed by heuristics. Well, the data-driven techniques means that the augmentation strategies are learnable from the input data. So in each dimension, we will introduce several recent works. After the general introduction, so let's step into the second part of our tutorial, the natural dynamics in graph neural networks. So again, there are 5 aspects we will cover in the natural dynamics. So let's first go to the temporal graph neural networks with convolutional operations. Please note that since we are going to cover many works in this tutorial, and different works may have the same symbols to represent different meanings. So to elevate this problem, in each individual work, we will introduce the meaning of the samples from the scratch. So the first research work about convolutional operations is called spatial temporal graph convolutional neural networks, or ST-GCN for short. The task is to obtain the graph level representation learning, and the goal is to use that representation vectors to do the temporal graph classification, where the natural dynamics means that the structures are evolving and also the node features are evolving with the time. So to be more formal, in this work, we aim to realize the skeleton-based action reconstruction, also called temporal graph classification in the graph research community, which means that given a sequence of skeleton, we first model them into a sequence of graph snapshots, also called a spatial temporal graph. So then this spatial temporal graph will go through the spatial graph convolutional network for the representation learning to obtain the high-level feature map. So after that, a readout function realized by a multi-layer perceptron, for example, is used to read out the category probability for the action classification, or we call graph classification. So as shown in the figure, a sequence of video snapshots are classified as the running action. So to realize the action classification or temporal graph classification, the first thing is that we need to model the actions into graphs. So in this paper, an undirected spatial temporal graph G for n human joints and t time steps are expressed as follows. So this spatial temporal graphs models the intra-body and the inter-frame connections. So what does this mean? So first, let's look at the node set, where each node set we have a node indexed by VTI, and T means the time step from 1 to capital T, and I means the node index from 1 to capital N. And we have the F function of VTI, which stands for the node features of a node, maybe the coordinate vector or the estimation confidence or something, etc. So for the intra-body or the intra-snapshot connection, we have the ES. So ES is the edge set. So the edges are node connections in the single time step T. So you can see the VTI and VTG. They are the node I and node G connections in time T. And also we have the interframe connections, which is denoted as EF. Well, EF is another edge set. The edge there represents the trajectory of a single or a same node over the time. For example, you can see the VTI and VT plus 1I. So which means the particular joint or a particular node. Joint means the joint of a human, for example, the elbow. So a particular joint or a particular node I, its trajectory over the time. So for the spatial temporal graph representation learning, let's first start with one single frame, which is denoted for, let's say, T, and see how the neighbor information are aggregated. So in the following equation, if we want to obtain the representation vector f out for the node VTI for the node I and time t, so we need to look for the we need to look for its neighbors in this single frame T. So BTI denotes that the set of neighbors of VTI at time T. So those neighbors are selected based on the feature distance as shown in this equation. So for a node VTG in the neighbor set, so f in VTG is the function. F in is the function to read out the feature of the node VTG. So where the term ZTI VTG is the normalizing term, so which reflects the number of nodes that are equivalent to the node VTG towards to the central node VTI. So since all the observations above are executed in one single time t, so actually they can be realized by the GCN or graph convolutional neural network as the backbone model. Beyond searching the neighbors in the single frame at time t, the next question is to ask, how can we aggregate the information from temporal neighbors across different time steps? To realize it, the corresponding operation in st-GCN is easy to understand. So recall the function we just introduced in one single time frame. So we just need to enlarge the scope of the neighbor selection. So correspondingly, the neighbor B VTI is upgraded as follows. So given a hyperparameter controlling the time window, we also collect the neighbor from other time steps, which means that if it is close to the center node at the current time step. To be more specific, as shown in this formula, if VTG and VTI are neighbors in time t, then the trajectory of VTG are also the neighbors of VTI. So after introducing the st-GCN framework, we know that it considers the intra-snapshot edges and the inter-snapshot connections. But for the intra-snapshots, st-GCN assumes that all connections in one single snapshot are appeared simultaneously. So is that possible that edges in one snapshot actually have different time steps? So according to a recent study, so the answer is yes. For example, in the dynamic protein-protein interaction network of yeast cells, so it may have 33 continuous observations that are 33 edge steps, and every 12 observations compose a metabolic cycle, which means we have three snapshot time steps in total. So which also means in one single snapshot, 12 edge time steps exist. So given the multiple edge time steps, given the multiple time steps coexist in a temporal graph, so how can we still achieve the temporal graph classification based on the graph neural networks? So to do this research, so at least three questions need to be answered. So first is that how to integrate the multiple evolution patterns that are multiple time steps. And the second research question is that how could we encode them for an embedding for the temporal graphs such that we can do the classification. The third research question is that labeling graph is usually costly, especially for the time-evolving graphs. So how could we leverage fewer labels, but using them effectively? So facing those about questions in our recent research called TEMP GFSM, so we propose 3 components to address those challenges one by one. So they are multi-time evolution, multi-time attention, and temporal graph few-shot metric learning. So you can understood the multi-time evolution as a fundamental modeling to model the multiple dynamics that are multiple time steps. For the multi-time attention, you can understood that this is a mechanism to weighting multiple dynamics when we learn the graph representation vector. And the third part is that how could we use fewer labels to do the temporal graph classification. So the first 2 parts are relevant to our tutorial. So let me give you some details about that. So in the multi-time evolution of temp GFSM, an edge is marked as a quadruplet, which is VI, VG, TE, and TS. So the TE means the edge time step, and TS means the snapshot time step. VI, VG, TE, the triplet, means that the connection between VI and VG exists at the edge time TE. And the VI, VG, TE, and TS, this quadruplet means that the event VI and VG, TE, this edge connection happens in the snapshot of the TS. So this is the multi-time attention framework of the temp GFSM, so which has 3 attention mechanisms. So the first one is node level lifelong attention, which the second is intra-snapshot attention, and the third is inter-snapshot attention. So imagine that you are writing an article. So the node level lifelong attention is something like you are selecting the meaningful words. And the intra-snapshot attention is something like you compose a supportive sentence. And the inter-snapshot attention means that you finish the fluent articles with particles with paragraphs. So this work is more based on the attention mechanism. So since we are in the convolutional part of our tutorial, so we will introduce the corresponding attention techniques in the later of our tutorial. Then let's look at the second graph convolutional operations of temporal graphs. So let's then introduce the research work called spatial temporal graph convolution networks, which is STGCN for short. So difference from the previous one, this one is called STGCN without the dash. So the task in STGCN is to achieve the node feature prediction given the evolving node features under one latent graph structure over time. So to be more specific, STGCN is designed for the traffic forecasting. So this is given the past traffic flows. We are going to predict the future traffic volumes or traffic flows with a latent graph structures. And the graph structures is the road connections in a certain location. So with this objective, VT here means the vector, which is a observation of n rows, like the traffic volume or traffic density of n rows captured by the sensors. So n rows here means that there are n nodes during the graph modeling. So W here is the weighted adjacency matrix of the road network. So each node represents one road segment. So this adjacency is static, which means it's shared over all time steps. So first, similar to ST-GCN, ST-GCN here also has the spatial feature extraction module, which can also be realized by the GCN backbone. Different from the ST-GCN, ST-GCN here does not search for the temporal neighbors to aggregate the temporal features. Instead, it uses the time convolution on temporal features. For example, the VL as expressed as follows. So VL is a concatenation of the node features VT. And recall that VT here is a n-dimensional vector, which means the temporal features of n road at time t. Then let's decompose this equation and figure out how the time convolution works. So let's disentangle this equation from the right-hand side to the left-hand side. So the first time we are looking at is the VL. So the VL is the stacking of the VT minus M plus 1 until VT. And L here means the index of the unit block or the layer of the ST-GCN model, which means we are getting the VL plus 1 from the VL. And the asterisk T means the time convolution of those temporal features. The detailed operations will be introduced in the next page. And the asterisk G means the graph convolution. And you can understand it as a GCN backbone. So after a ReLU function, we go through another time convolution such that we can get the VL plus 1 from the VL. Next, let's look at the time convolution and figure out how it works. So let's dive into the time convolution operation in the ST-GCN. So of course, a quick win solution is that we didn't use the time convolution, but just stack all the temporal features as VL and then put it into the graph convolution. But the advantage of applying the time convolution on VL is that a 1D kernel along the time axis could aggregate the temporal neighbors to capture the temporal behaviors of features. For example, the traffic flows, especially for the long-term time series analysis. So far, we have finished the temporal graph neural networks with the convolutional operations, and we will step into the next part, the temporal graph networks with recurrent units, to see how recurrent structure get leveraged to deal with the temporal information for graph neural networks. So before we step into that part, so do we have any questions from our audience? Okay, great. Let's move on to the second part of natural dynamics. So here we will introduce the research work about temporal graph networks, neural networks with recurrent unit called diffusion convolutional recurrent neural network, or short for the DCRN. So which means we aim to achieve the node feature prediction through the node level representation learning under the node feature are evolving along with the time. So here is the formal problem definition of DCRN work. Still, like we are focusing on the traffic forecasting, we have the feature from past, for example, the t minus t prime plus 1 until t, and with a latent timely shared graph structure. And we are going to learn a H function to predict the future features for example, the traffic volume. But the difference from the DCRN to our previous discussed STGCN, so the difference are, what if the latent graph structure is directed? And the second difference is that how can we deal with the time information other than the time convolution? For example, how could we take the time information recurrently? So let's first look at the first question for the directed graph structures. In DCRN, 3 modules are designed for accomplishing this task. The first one is called stationary distribution of the diffusion process. The second one is called diffusion convolution. And the third one is the diffusion convolution layer based on the diffusion convolution computation. So let's step into each one of this. So the stationary distribution of the diffusion process can be represented as a weighted combination of infinite random walks on the graphs. So this is the formula. So how could we understand it in depth? Also, let's decompose this equation from right-hand side to the left-hand side. So the K here means the index of the random walk step. So which means that we have the K equals to 0 from the infinity to stand for the we walk randomly many more. And the W here means the, as we just discussed, the weighted adjacency matrix. And the DO here means the alt degree diagonal matrix instead of the standard diagonal matrix, since that here the graph structure is directed. And the alpha is the personalized probability in the random walk. So after the power iteration or the infinite summation of the diffusion process, we get the matrix P. So in matrix P, the ith row represents the likelihood of the diffusion, or you can stand it as the personalized page rank vector, starting from the node I as the interest node. So with the diffusion introduction, so we can based on and a filter. So what is a graph filter? What is a graph signal and a filter? So graph signal you can understood it as a feature matrix, where n is the number of nodes and p is the node feature dimension. And f theta, you can understand this graph neural network filter as a learnable parameter, which is weight matrix in the graph neural networks. So with this introduction, we have the following equation. We have a x as the feature, as the node feature, and asterisk g as the diffusion convolution, and f theta as the weight matrix. So how could we understand this equation? Again, let's decompose it. So now we have decomposed it as follows. Also, we go over this equation from the right to the left. So XP here means the feature matrix of a certain node P. Of a certain dimension P. So with this node feature, we have the in-degree diffusion and out degree based diffusion. So for the in-degree based diffusion, again, we have the similar as we just discussed, the weighted adjacency matrix, the in-degree diagonal degree matrix. And for the out degree based diffusion, we have the, again, weighted adjacency matrix and out degree diagonal degree matrix. For each in degree and out degree diffusion, we prepare a parameter as the weights to project the diffusion to project the diffusion we just computed. And then we have the iteratively like the random walks. So based on the diffusion convolution computation, we can now ready to introduce the diffusion convolution layer that could map the p-dimensional features to the q-dimensional outputs. So again, let's move to from the right to the left. So we have the f theta qp comma comma, which is the parameter here. So the last two comma, the last one comma is the index for the in degree or odd degree diffusion, which means 1 or 2. And also the second comma is the parameters dimension for the k, which is the random walk steps of the which is the diffusion steps, or you can understand that the random walk steps. And also we have the asterisk g, which is the graph, which is the diffusion convolution. And also we have the input features x. So after a activation function such as ReLU or sigmoid, we have our output h for the downstream tasks. So after we introduce the directed graph structures with the stationary distribution, diffusion, convolution, and its layer, the next question is, how could we take time information recurrently? So in this work, a technique called temporal dynamics modeling is proposed. So the general idea of the temporal dynamics modeling is inspired by the recurrent structure or the recurrent architecture called gated recurrent units, or GRU for short. So the key point here is how to make GRU take the structure information or the graph information. So the basic GRU architecture has the input, the reset gate, the update gate, and the output. So as shown in the following, shown in the red figure, so we have the input xt and the hidden state ht-1. So going into the GRU architecture, we have a update gate output a certain hidden representation, and we have the reset gate outputting a hidden representation. And we combine these two hidden representations to get the output and the new hidden representation state, ht. So this structure may be complicated to understand from my words. So let's look at how it got modified to take the structure for the graph convolution. Sorry, for the graph diffusion. So again, we have the input xt and ht-1. So the reset gate here is the graph diffusion convolution operation. So which means we concatenate xt and ht-1, and then we use the graph convolution as the ancestor asterisk g and a theta r. So this is the standard formula we just discussed in the diffusion operation. So also for the update gate, the structure is similar, but the parameter here is changed from theta r to theta u. So these two are the same structures with similar parameters. So the output is that we combine the output from the reset gate and the output from the update gate, and combine them to get the hidden representation for the next time step and the output for the current time step. So let's check out the performance of the DCRN work in the traffic forecasting. So before we start introducing the experiments, let's check out the data sets they used in this paper. So in this paper, the authors used two data sets from the road network. So the first is called METRLA, so which is the highway road network of the Los Angeles. So in this graph or this road network, we have 207 sensors, and each sensor is recording the traffic speed of a road segment. So the time series is recorded from the May 1st, 2012 to the June 13th, 2012. And the second second data set is called PEMS Bay, so which is the highway network in the Bay Area of California. So in this network, we have 325 sensors. Also, each sensor is recording the traffic speed of a road segment. And this time series is recorded from June 1st, 2017 to the May 31st to the 2017. So the performance here, we can see that the first column instead of stands for the how the time interval we are going to predict. For example, we have the 15 minutes, the 13 minutes, 30 minutes, and 1 hour minutes at 3 different time intervals. And to predict this, we can observe that from this table, the DCRN model achieves the best performance with all 3 metrics for forecasting for different forecasting intervals or forecasting horizons. So the metrics are the reconstruction error from the predicted and the ground truth. So the advantage of the DCRN becomes more evident with the increase of the forecasting horizon, which means that for the 1 hour prediction, the performance gain of DCRN is large from the 10 to 7. So DCRN is different from all these methods due to the formulation of the convolution of the diffusion convolution of the graph. So authors model the sensor networks as a weighted directed graph, which is more realistic than the grid or undirected graph, as the author claimed in their paper. So in DCRN, the adjacency matrix, or the weighted adjacency matrix is shared across the time, which means it's static. But also this adjacency is handcrafted, which means that the edges are connected or not, based on the distance of the 2 vectors from the 2 row segment, or as we see the nodes in the graph. So which means that if the distance is close, then a threshold, then these nodes are connected. If not, they are not connected with the corresponding weights. The next spontaneous question we may ask is that, could we find another way to extract these latent structures instead of using it as this handcrafted one? So to answer this question, we are going to introduce a recent work following the DCRN, which is called Discrete Graph Structure Learning for Forecasting Multiple Dynamics, or GTS for short. So focusing on the same problem setting, which is traffic forecasting, and the same diffusion convolution structure as DCRNs. So in GTS, the graph G here is no longer static across all time steps, which means that according to each time step, we may the graph structure in GTS is still static, but we are not defining it as a weighted connection as prior knowledge, but we are going to learn it along with the forecasting process. So how do we learn the adjacency matrix along with the forecasting process? So here, the authors model the adjacency matrix as a parameters to learn. So in this equations, Aij means the adjacency between node I and node G, and they are decided mainly by the theta Ij. And what does theta Ij mean? Theta Ij means that the vectors of Zi and Zg of the Zi and Zg means the hidden representation of node I and node G. And Zi is obtained through a feed-forward neural network of the time convolution of the xi. And xi is the original input features of the ith node over all features and time steps. So which means that also the connections are based on the nonlinear projection of the input features. And after we have the theta Ig, the Gig here are the samples sampled from the Gumbel distribution to introduce some bias during this learning. And S is the temperature for the smoothness. In this way, the data structure is learned along the prediction process. Then let's check out the upgraded performance of the traffic forecasting provided by GTS. So comparing with the DCRN, the GTS achieves little or better performance than the DCRN, which means that the learning or the learning process of the adjacency matrix is more helpful than we set it ahead of the learning process. After we introducing the work, DCRN and GTS, we know that in their works, the adjacency is fixed with the evolving node features. But a natural or a spontaneous question is to ask, what if the adjacency is also evolving together with the node features, which means at each time t, we may have different adjacency matrix and different node features. So to answer this question, a recent work called EVO GCN is proposed for the evolving structures and features. So the EVO GCN is proposed to adapt the model parameters, which means that to be specific, at each time we have its own GCN model trained solely on the adjacency matrix AT and HT. But cross time steps, the model parameters are dependent, which means the current model parameters are dependent on the past parameters. So to achieve that, the authors here use the recurrent structures to adapt the weight matrix or parameters of the GNN models. For example, the WTL will be the LSTM output of the WT-1L. Well, the WTL means the parameter at the else layer at time t. So after addressing the question, what if the adjacency is also evolving? Another spontaneous question is to ask, can we predict the future adjacency instead of we just predict the future node features? So for the evolving features, structures and features, a recent work called VGRN is proposed to learn the variational posterior distribution of the evolving adjacency structures together. So which means that also this model is encoded in the RN structures, which means that the latent distribution could refer the adjacency matrix in the future. So due to the time limitation for the evolved GCN and VGRN, we didn't give it a very detailed introduction, but we list the reference for your interest to check it out after our tutorial. Now we have finished the introduction with the temporal graph neural networks with the recurrent neural nets or the recurrent structure or architectures. So before we move into the third part, do we have any questions from our audience?
Hello.
Hi, I can hear you.
Yeah, thanks for your interesting part about recurrent nets. Actually, I have one simple question regarding the connections between the work. So I see actually, for example, this kind of evolving adjacency matrix is actually older than the discrete adjacency matrix, which is fixed. I mean, how is the order of the work is, the order of publishing is different from the order you are showing. I mean, so I mean, you got my question?
Yeah, I suppose if I understand your question clearly, so you are asking if they follow the chronologic order for publishing their papers?
Yes.
Okay, so based on my knowledge, so the first attempt to deal with the dynamics or the evolving features or evolving topologies in graph neural networks starts from the convolutional operations or the GNN structures. And follow that, we step into the area of the recurrent neural networks or the RN architecture. So after the RN architecture, we step into the stage of the self-attention mechanism. So in the self-attention mechanism, we have the time attention mechanism and also the time kernel functions as the part of the attention mechanism. And also we have the temporal point process as the attention mechanism. So after the recurrent introduction, we will step into the self-attention mechanism and see how the time kernel and time point process help the self-attention mechanism during the temporal information for the graph neural networks.
Okay. Yeah, another point I'm mentioning, especially for recurrent units. So you have mentioned, for example, the discrete graph with fixed adjacency matrix. Then you have mentioned like as a solutions, like either to update the adjacency matrix or the variational graph recurrent neural network with evolving adjacency matrix. So I'm asking is that because, for example, the fixed adjacency matrix paper is newer than the evolving adjacency matrix. So I'm asking how this. I mean, if for example VGRNN is already solved the problem, then how the discrete graph structure learning paper, because it used fixed adjacency matrix. It's using the older version, even it's published afterwards. You got my question?
I didn't fully understand your question. Maybe you can, say it again. Yeah.
Yeah, I mean,
you
see reference three, variational
yeah,
graph
yes,
linear. This is
yeah,
suppose the best actually approach for addressing the problem by evolving adjacency matrix, right?
yes.
Reference two is actually using the fixed adjacency matrix, right?
Yeah.
Although reference two is much newer than reference three.
Yes, yeah. Yeah, maybe I understand your question. So the published year may not be the evidence of the technical advance because when you submit a paper, it maybe get rejected from the conference, even though it's have the better performance or new problem standing point. So the maybe sorry, did I answer your question, or you may
Yes,
have
yes,
other?
yes, 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 yes. Thank you.
Okay, thank you for your questions. Uh, so let's move on to the third part of natural dynamics in graph neural networks. So this is called the temporal neural networks, graph neural networks with time attention mechanism. So in this part, we will introduce a work called DYSAT, which is deep neural network representation learning on dynamic graphs via self-attention. So this work is aimed to achieve the link prediction through the node level representation learning with the evolving graph structures and node features. So this is the formal problem definition of the DYSAT, so which is link prediction. The first thing we need to do the link prediction is that given a sequence of graph snapshots from G1 to G capital T, which means each GT has its own adjacency matrix and feature matrix. So DYSAT aims to learn the node representation EVT for the node V at time t across all time steps from 1 to capital T. Then the latest time node embedding EVT and EUT are used to decide if there is an edge links node V and node U at time t plus 1. This is the problem definition for the DYSAT here for the link prediction. Also, in DYSAT, we know that there are two modules. The first one is structural self-attention, and the second one is temporal self-attention. So the key point of the structural self-attention is to apply the attention in one time step. And the challenge is that how we find the temporal neighbors to attend for a node. And for the temporal self-attention, also we need to apply the attention mechanism across time steps. But the challenge is that how we find the temporal neighbors to attend for a certain node. So let's first check out the structural self-attention. So at a time step t, so in the following equations, the superscript of t is omitted for the clearness, for the clarity. So the general idea here is to attend over its, for a node, the general idea is to attend over its topological neighbors in one single time step. So how could we do that? So let's focus on this equation about EUV here. So in EUV here, the bottom equation, we have the input features for the node U and node V denoted as XU and XV. Then we have a projection weight matrix for the structural tension, which is WS. So we times WS we multiply WS with XU and multiply WS with XV. Then we concatenate these vectors and pass it through a learnable weight matrix. After this projection, we times this to the adjacency matrix to get the initial attention weights, EUV. And after a softmax normalization, we got the AUV attention weight from the initial one, EUV. And after we got the attention weight, AUV, then we know that we can do attend. We can do attention. So for a node U, we have its node feature XU, and its neighbors stored in the for a node V, we have its neighbors NV, and for each node in NV, we times the input node features with the attention weights to get the hidden representation of the node V at the current time step t. So what we just introduced is in one single time step, The next necessary step is that how could we do it cross time step? So this technique called temporal self-attention. So to do the temporal self-attention, the question to ask is that who are the temporal neighbors for a certain node? So the answer in this paper is that temporal neighbors of a node V consists of its historical behaviors. So what does this mean? Also, let's focus on the initial attention, EVIG. So here we have the XV, where XV is the node feature across the time steps. For example, XV is a concatenation of XV at time 1, XV at time 2, and XV at time capital T. So we have the XV here for its temporal behavior of a certain node. Then we time it with a query matrix, which is a standard technical logic of the self-attention. So we time the XV with the WQ and XV with the WK. So F prime here is the normalization factor. So to obtain the attention weight of V from time step I to time step G as EVIG, we also add a matrix called IG to enforcing the auto-regressive manner. So which means the current time step can only attend its previous behavior. So this MIG formulation will be introduced in the next page. So after we get the initial attention weight, EVIG, again, we smooth it across all the time steps to get the attention weights, which is decoded as beta VIG, which is the attention weight from node I to node G, these two time steps. And from beta IG, we have the beta V as the matrix, which dimension is T times T. And we have the XV is the node feature T times the input dimension, and the WV is the input dimension times the output dimension. So after that, we got the DV. We got the ZV. ZV is a node V's time embedding from all the time steps of all features, which dimension is T times F prime. So then we can introduce what MIG means. So the MIG is simple to understand. So if I is smaller than G, then MIG equals to 0. Otherwise, it equals to negative infinity. So which means that when MIG equals to negative infinity, the beta VIG will equals to 0, which switch off the attention from the time step I to time step G. Again, it forces the learning follows the auto-regressive, which means the current step can only attend its previous time steps. So after we introduce the structural and temporal self-attention, how could we combine them together to obtain the structural temporal attention attention-based representation learning for a certain node? So this is the architecture of the DY-SAT in this paper. So we have the two major parts of DY-SAT. So the first part is that we obtain the structural encoding or structural embedding independently at each time t. Then after we get the embedding of each node at each time t, then we can do the temporal self-attention to attend over the time steps. So this is how we aggregate the temporal, or we combine the structure and temporal self-attention together in DY-SAT. Is this all together? Is this all for the DY-SAT? Maybe not. So if you zoom in this architecture, we can find a P here. So the P here in each time t stands for the positional encoding. So what the positional encoding do, or what does the positional encoding do in this architecture? So the positional encoding is originated from the NLP community, from the self-attention or the transformer architecture. So which aims to add the absolute position constraints. So in our setting, so which is aimed to add the absolute temporal position constraints. For example, for the HV time 1, we have to add the positional encoding P1. For the HV2, we have to add the positional encoding P2 to constrain the whole learning follows the time order. So how the positional encoding compute? How could we compute it? So let me give you an example. So this picture is still from a blog, so which we can see if we have a 0 as a position. So then we have the positional encoding function as sine, cosine, sine, and cosine. So then 0 will be encoded in the temporal in the positional encoding as 0, 1, 0, 1. So if we have another positional encoding function for the position 1, we have the 0.84 or 0.54 and 0.1 and 1. This is the general formula of the positional encoding. So then we finish the graph neural networks with the self-attention mechanism adaptation, which is called time adaptation mechanism. So then we will introduce the time kernel and the temporal point process, which are highly related to the time attention. So do we have any questions from our audience? Great. Let's get started. So back to the
oh, so sorry. Wait a minute. Our audience has a question.
Oh, sorry. Yep.
Hi, Tong. Thanks for the great presentation. So I have a small question about the attention mechanism in modeling the time series data. So I think you have present a lot of wonderful work that using the attention mechanism for modeling the temporal graphs. And also this kind of mechanism can be used for the spatial temporal traffic forecasting. But recently I found there are some research published in the AAAI, and they claim that the transformer, the attention mechanism such as the transformer cannot well handle the time series data, especially for the time series spatial temporal traffic forecasting. So do you have any opinions on this kind of research finding? And what do you think the abilities of the attention mechanism like transformer for the spatial temporal traffic forecasting or time series forecasting?
Yeah. Thanks for your question. So very interesting observation. So basically from my understanding, the temporal attention has also the great performance in several tasks for the time series analysis. But as you see that there is some new trending research projects saying that temporal attention may not be that good. So also in our tutorial, we actually have, maybe in the following part, we have the, here you can see, which is a new paper published this just a few months ago in the iClear, so which is called, do we really need the complicated architecture like the attention for the temporal networks or the time series prediction. So in this paper, the conclusion is not that necessary for the time attention. So they just call the MLP architecture for the time series analysis within the temporal networks. So back to your question, is temporal time attention always the panacea for the time series analysis? I suppose it's currently maybe yes, but in the future it may be not. Yes, and for the future, we have the wide space to investigate. So which one is the state-of-the-art approach for the time series analysis within the temporal networks.
Yeah, thanks for the question answering. So another question is, you only mentioned about using the attention for modeling the to capture the temporal information, but do you think there are any abilities to use the attention mechanism or the transformer structure to capture the spatial information, like using the graph formers for capturing the spatial information, or combine using attention to simultaneously capture the temporal and the spatial information?
Great. Yeah, so the in the research work we just discussed, DYSAT, so which separate the spatial attention with the temporal attention. So in the next work, time kernel, so where there is a work, is just collect the as you said, simultaneously collect the neighbors, considering both time relation and spatial relation. So after they collect those neighbors, they attend those spatial temporal neighbors instead of like DYSAT just did the separate two parts.
Okay, great. Thanks for answering.
Thank you for the question. So let's step into the the fourth part of the time kernel. So back to the positional encoding, do we have other options instead of we have the better formulation for the positional encoding? The answer is yes. So the network, the work we are going to introduce is the inductive representation learning on temporal graphs, or TGAT for short. So TGAT can be realized for the link prediction or the node classification through the node level representation learning with the involving graph structures and node features. So in TGAT, the kernel function or the time kernel function is proposed to map a time t to a finite dimensional representation vector. For example, in this formula, we can see that we have a time t, a scalar, and then we have omega 1 to omega d, d parameters. So then we can encode the time t to a representation learning for this scalar. So suppose there is a target node v0 at time t. So we need to attend its spatial temporal neighbors, as we just got the questions from our audience. So the n v0 and t is the spatial temporal node set. So which means that for each node vi, v0 connects with it previously at a different time step. For example, v0 connect vi at ti, and v0 connect maybe vn at tn, something like that. So each connection has a different time step. So also to attend the spatial temporal neighbors, let's need to prepare some warm up. So first, to be specific, we need to form the GT. So how do we form that? We can express it as follows. So the H0 L-1T means the node embedding of V0 as the L-1 layer of TGAT, and the zeros layer is the initial input feature. And the phi dt0 is the time kernel function, which maps the 0 to a representation learning to the representation vector. Also, we can map the t-1, this scalar value, to a d-dimension or 2D dimensional representation vector. So then we have n+1 actually vectors, and we stack it into a ZT. So ZT is the intermediate step of getting the node embedding H0 at the else layer of TGAT, which equation or the formation can be illustrated in the right-hand side figure. So with the spatial temporal neighbors and the ZT, So next, we can do the self-attention on the spatial temporal neighbors. So the ZT, following the standard architecture, we need the query key and value matrix for the self-attention. So again, ZT, the zeros row, and from the first row to the nth row, and first row to the nth row, then we can form this by multiplying with the WQ, WK, and WV to form the QKV matrix in the self-attention mechanism. And then we can just call the attention on the QT, KT, and VT to get the HT. After we have the HT, we can times it with the weights and bias after two feed-forward neural networks to read out the representation vector of node V0 at the else layer of the TJAT. So this is the logic of the TJAT work. Are there any other form of temporal? Are there any form of time kernel functions we can use in the time self-attention mechanism for the temporal graph neural networks? The answer is also yes. So in this paper, we have listed several time kernel functions, and the third one is used for the TJAT, and also others are going to be explored in the future directions. So after we have introduced the time kernel functions, we will step into the temporal point process, the last part of the natural dynamics of graph neural networks. Yeah, before that, are we have any questions from audience? Great. Let's continue the last part. So in this part, we will introduce the work about DYREP or the DREP for the learning representations over dynamic graphs. So this work is going to achieve the link prediction via the node level representation learning with the evolving graph structures and node features. So fundamental introduction is needed for the temporal point process. So what short for TPP? So what TPP means? You can understand it this way. So a user is tweeting. So they tweeted at time T1, which is 8 o'clock, and T2, which is 10 o'clock, and T3, which is 11 o'clock. So what is T4? What the next tweet will be? So the TPP is this kind of model that could fit this process of T1, T2, and T3 to predict what is T4, maybe the 12 o'clock. So mathematically, the TPP is formed as follows. Given the history of events, HT is consists of the T1 to the Ti-1, which have the I events. So with this history of events, we need to model a conditional probability density function f, which is ft given ht, which is a conditional probability that the next event will occur during the interval t plus during the interval t to the t plus dt. So a cumulative distribution function, capital Ft, is the integral of the last event to the current event. So which is the conditional probability that the next event will occur before t. So a complementary of capital Ft is denoted as St, which is the conditional probability that the next event will not occur before time t. So in this figure, we can have a better illustration of this modeling. So the Ft here means the next event t will occur during the interval t to the t plus dt, which is the green area in this figure. And the capital Ft that the next event will occur before t, which is the blue area of this figure. And St is called it represents the next event will not occur before the time t, which is the pink area plus the green area. So the most important part of the temporal point process, or TPP, is that we can use the conditional intensity function to model this process. So which is denoted as lambda t, which is a conditional probability that the next event will happen during during the interval t, or t plus dt. So which is defined as follows: lambda t is equals to the ft divided by the capital ST. So which you can understood as the area of the green area divided by the green area plus the pink area. So how could we understand lambda t? So lambda t can be also understood as the instantaneous rate of events per time of units. For example, the 10 twists per minute. So using the form of lambda t instead of the complex modeling in the previous slide have also other merits, like the model parameterization and model reusability. So the next important question is that how could we model or compute the lambda t? So there are different variants of temporal point process. We have the homogeneous portion process, which is a lambda t equals to a constant over the time, which you can understand that always 10 twists per minute. Also, we have the inhomogeneous portion process, which is a nonlinear projection of time t. So you can understand that we have two twists at maybe 8 o'clock in the morning and maybe 25 twists at the afternoon. So also we have another kind of inhomogeneous portion process called Hawkes process, which is more a little bit more complicated process. So the parameters of the intensity function lambda t can be obtained by fitting the model with the observation in the real world and maximizing the log likelihood. So the next part is that how could we model the temporal point process for graphs? So in this work, each edge connection is considered as an event, which is denoted as u, v, and t. So we want to predict whether a node v and whether a node u and node v will connect at time t, given node u's history and node v's history before t. So to do this kind of problem, the formulation is quite simple, and we can understand that easily. So the lambda here means the intensity function of the connection of u and v at time t. So the t bar here means the time steps just before the current event that uv just connects. So the inner function g computes the compatibility of the concatenation of the node vector du at time t bar and the node vector gv at the time t bar. And the outer function f here is a soft plus function with a trainable parameter to make sure it outputs the positive values. So now the question is, how could we get the node embeddings in this function, which is, for example, the EV at T bar? So to obtain the node embeddings like EV T bar, in this work, the authors design three techniques, which is called self-propagation, which is used to consider the historical behavior of a node, and an exogenous drive, which is designed for the smooth update for the current event. And also the third and the important part called localized embedding propagation, which can be understood easily as the message passing within the second order proximity. So this is the function of getting the node vectors, node embedding vectors. So the self-propagation and the exogenous drive can be understood easily. For example, the 2 time minus and times transition projects times projection matrix with WT. So the TVP bar here means the time that for the piece event of node V at time t, and the TP is the current time we want to predict for the event. And also, please note that for the TVP bar, there is also another time step called TP bar, so which is responsible for the localized embedding propagation. So this part is more complicated. We will introduce it in the next slide. So the localized embedding propagation, the first component of this equation has the W construct. W struct is just a learnable weight matrix. So the HU struct is the aggregation of node U's neighbors. So recording the event happens between node V and node U. To obtain the node V's representation vector, we also need the neighbor information from node U. So this is the intuition of this localized embedding propagation. So to get the neighbor information aggregation from node U, we have the following equation, HU struct T bar. So the T bar means that any event happens previous to the TVP bar. And to do this, HU struct T bar is a max pooling function to read out the you can understood as a tension over the neighbors of node U. Well, HI T bar means each node I in the U's neighborhood, and we have their attention weights or the connection or the edge connection weights. We read out the max component in this neighborhood, and as the second order proximity of node U to get the node representation for the node V. So yeah, since we almost finished the last part of the natural dynamics, we have almost finished the second part of the whole tutorial, the natural dynamics in graph neural networks. Also, due to the time limitation, there are also many great research works on natural dynamics for graph neural networks. For example, they have the contrastive learning across different time steps, or the fast computation techniques, or the simplified architectures for the temporal networks. So for the limitation, we do not have time to go through these great works, and there are also many more great research works about natural dynamics and graph neural networks. Yeah, so we have finished the second part. We will step into the 30 minutes coffee break. So before we do that, we can also very glad to answer any questions from our audience.
Hi, Dongsi. Can you hear my voice?
Yeah, I can hear you.
Thanks so much for the presentation. So yeah, I have some couple of questions here. Actually, this is the new area for my research in terms of dynamic graph neural network as well. So I heard some couple terms that might confuse me. Like there are some couple dynamic graph network as well, like spatial temporal graph representation learning, dynamic graph representation learning, and as well as I heard some couple terms called continual graph learning as well. And as I remember at your presentation before, you mentioned always like we have a fixed number of nodes And then my question is, how if we have a newly appear node, so how we can accommodate that node into our new dynamic GNN models? And suppose if we have a new node, and then do we need to relearn that spatial information before? And if we have like the large scale graph representation, what do you think about the efficiency of the learning process itself? So yeah, maybe you can give me some advice about that
Yes.
one. Yep.
Yes, thank you for your question. So the first question you are mentioning that if we have the newly inserted nodes, how do we deal with this scenario? So the answer here is that basically we have the time representation for the discrete time or the continuous time. So for the discrete time, which we have each snapshot of at each time step. So for your questions, what if the newly inserted nodes? So during the research, the common solution is that we assume that have the same dimension across the time step for the dimension consistency. A newly inserted node will be a dangling node in the past. So this is the solution for the discrete time. For the continuous time, this is not a very big problem because we do not need to store the adjacency matrix with a certain dimension at each time step. We just store the node level, at the edge level insertion or deletion during the evolving of graphs. So based on the tutorial, we have introduced several works. So some of them are based on the discrete time, and some of them are based on the continuous time. So when you face the each method have its pros and cons. So based on your specific problem setting in the future, you may choose the continuous time or the discrete time for research. And also for the second question, if I remember correctly, so is there any for the large scale for the second, I remember that. For the second question, that what if the newly inserted newly inserted nodes, how could we learn the representation learning for the newly inserted nodes? So this is also a very good question. So there is a technique called, or the difference between the techniques called transductive representation learning or inductive representation learning. So the scenario you are mentioning is more like the inductive representation learning. For example, we can have the here. The inductive representation learning means that based on the heuristic, based on the previous representation learning process at the past time steps, we can deal with the newly inserted nodes, just collecting from the previous node representations and obtain it only if it just connects with several nodes at the current time step. So this is the logic or the philosophy of inductive representation learning in this specific work. And so the third question you mentioned that for the large scale temporal graphs, how do we learn it effectively and efficiently at the same time? So it varies, which means it depends on the architecture of the neural networks. For example, in the here, the SDG, simplified and dynamic graph neural networks. So this paper is based on the PageRank based or the random walk based scheme of the graph neural networks. So when the graph is large and the graph is evolving, so instead of compute the transition matrix or the message passing matrix from the scratch, we can just fast track the solution. So the track method is based on the PageRank tracking method, which can have the theoretical bound of the time and the computational efficiency. So This is the to the best of my knowledge, it's based on the architecture you are using and facing the large-scale evolving structures. So there are some fast solutions to approximate this solution instead of solving it from the scratch. Yeah, it's based on the architecture you are using for the temporal graph representation learning.
Yep. Thank you for the answer.
Yeah, thank you for the question.
Okay, I'm the presenter of the second part, the second half of this tutorial, and we will talk about some techniques about the artificial dynamics in graph neural networks, and we will talk about some challenges and future directions. And at the end of this talk, there's a Q&A session. Okay, so this is the general picture about what we talk about artificial dynamics. So let's start from the motivation of why we need artificial dynamics. And after that, I will introduce two groups of the methods. The first one is heuristic-based techniques, and the second is data-driven techniques. And we carefully select 7 represented works. I hope you can get the core ideas of those works, and they are easily generalized to a versatile artificial dynamics in graph neural networks. So artificial dynamics is first defined many years ago, and it's named the artificial jumps. And it is proposed to modify the topology such that the results of the PageRank can be personalized. And in the modern graph neural network context, the artificial dynamics means to modify the given graph for some specific functionalities. For example, we can improve the scalability of the graph neural networks, or we can improve the expressiveness power of the graph neural networks, and so on and so forth. And this technique is also known as the graph data augmentation for graph neural networks. So why we need the artificial dynamics? The first example we provide is that the given graphs might not be informative. So here on the left-hand side shows 2 groups of people on the social networks, and both of them love playing soccer. And the one group of them are located at Chicago, and another group of people are located at Champaign, which is our school located at. So we are 2 hours away from Chicago, but we both love playing soccer. So if we want to recommend some friends over these social networks, because we are physically far from each other, we might do not know each other, right? So how about add some super links between those 2 groups of people? So because they share the same hobbies, they share the same features, such that the graph neural network can capture the similarity between those 2 groups of people to empower better recommendation results over the social networks, right? And the second example is that a given graph could be noisy and be poisoned. The example here we use is still on the social networks, but the function we try to achieve is the anomaly detection system. So when we use the social network, we are usually followed by some malicious or fake account, right? So they try to camouflage themselves by following some good accounts to show that they looks like a normal account, right? And that will challenge our anomaly detection systems because we don't want to have some fake followers in the social networks like the Instagram, right? So how can we do? For our system, if we can verify that some users are good accounts, then we can manually add some links between them to enhance the patterns in the good account, then push the graph neural network-based anomaly detection system to distinguish the good accounts and the bad accounts, right? And at the same time, we can also verify that if those users are the real friends in the are really the friends in the real world life, right? So if they are randomly followed by those fake accounts, then we can delete those links on our social network, such that in this case, this bad account, this fake account will be isolated and it's clear. It will be detected by our anomaly detection systems on these social networks. Right? And the third motivation is that the given graph could be huge. So according to these statistics,
they say that the number of Instagram users will increase over 40% in 5 years from 2020. And not to say that we have hundreds of thousands of posts and videos, right? And the second right-hand side is academic research datasets, which is named the Open Graph Benchmark. And you can see they contains over 200 million number of nodes in the node level tasks, and they contains over 3 million number of graphs. That's crazy, right? If we put them into the GPU, our GPU will be out of memory, right? So the question is that how can we shrink the size of the training graphs while keeping them informative as possible, right? So that's another motivation of the artificial dynamics. And for sure, there are many more motivations, and we will introduce later. So let's have a warm-up about the technique, which is from the heuristic-based techniques. And the first technique represented work we will introduce is named the job edge. So job edge is actually a very simple technique to improve the usefulness of the graph neural network. The task that this paper studies node classification, and the artificial dynamics they propose is very simple again, randomly removing a certain number of edges during the training iterations. Okay, so here the key point is that this technique is only used in the training iterations, and in the inference time, usually we would not use these techniques. Okay. And the goal is that they try to reduce the message passing of the graph neural network to alleviate a bad phenomenon we named the oversmoothing. And the mathematical operations that they will drop a part of the non-zero entries from the adjacency matrix. So here, let's have some background about why they proposed the job edge. Okay. This background is mainly about the phenomenon named the oversmoothing. So we will start from the convergence of the PageRank. So if we appropriately normalize the adjacency matrix as delta A, and we keep doing power iterations to continue the diffusion process, and we multiply this powered adjacency matrix with the node feature vector X, and we find that finally the diffused node vector will be converged to a vector pi. And the important part is that this converged node feature vector pi is independent of the selection of the initial node feature X. What does it mean? It means the given node feature is missing, right? So what's its relationship with graph neural networks? I select two representative works. The first one is graph convolution nets, and the second one is simplified graph convolution nets. So you can see the key difference between those two methods because it is the second SGC removes some nonlinearity in the intermediate layers, right? And because those two graph neural networks shares similar spectrum characteristics and empirical performance, so a lot of studies from the graph signal processing perspective will focus more on the SGC fashioned graph neural networks. And if we assume that the SGC contains many layers, then the formula will be shown as follows. So it is quite similar as what we did for the PageRank, right? We keep doing power iterations over the normalized adjacency matrix. And what will happen? Finally, we find the matrix within the nonlinearity will converge to another matrix, which is independent of the given feature matrix X multiplied W, right? So that's not what we want. Why? Because the given node feature is missing. Okay. So that's the background that why they propose drop edge. The drop edge operations is try to drop a portion of the edges in every training iterations. And clearly, if we keep dropping during every iterations, the convergence matrix will not be stable, right? That's the intuitive understanding that why drop edge can alleviate the oversmoothing. And also from the theory developed from the drop edge paper, they also show that after dropping a part of the non-zero entry from the adjacency matrix, the convergence speed of the population can be slower. But we will introduce in detail here. Okay. We will not introduce two details here. Also, let's see some empirical performance. So the first figure shows that if the graph convolution network is not equipped with the job edge, which is shown in the blue solid lines, and with the increase of the number of the layers, the distance between the intermediate node representations will decrease very fast. And that's not what we want. That's exactly what oversmoothing happens. But after the GCN is equipped with job edge, we find that the distance between the intermediate representations in the intermediate layers will be kept and not missing, right? And the bottom figure shows that after graph convolution networks equipped with the job edge, the training could be smoother. But if they are not equipped with the job edge, then the GCN training will get stuck, especially the number of layers are larger, such like larger than 5 or larger than 10. Okay. And the right-hand side shows some statistics about the node classification performance. So the authors of the job edge find that after the graph neural network equipped with this job edge technique, their performance can improve. And more importantly, they can handle the cases with high layers of the graph neural networks. And here I highlight a rectangle here, shows that under some cases, for example, the incept GCN, if they are equipped with 32 layers, the authors find that it will lead to a lot of memory problem. But after they equip it with the job edge, because they drop some non-zero entries from the sparse adjacency matrix, we can save some memory, so we can somehow improve the scalability of the graph neural networks. And there are some related works. So I think some audience already noticed that this technique is quite similar as the famous technique named the dropout, which randomly drop a part of the feature transformation matrix from the neural networks, right? So what is the difference? The difference, I use a single layer of the graph convolution networks for the comparison. The target of the drop edge is to drop a part of the entries from the adjacency matrix, while for the dropout, its target is the feature transformation matrix. Also, this technique is related with many sampling-based graph neural network like the GraphSage, FastGCN, GraphSync, and many more. And why they are related is because those sampling-based methods fundamentally drop part of the node from the given graph, right? And there are some other applications of drop edge. For example, it can improve, as we mentioned, it can improve the GNN scalability. It can alleviate overfitting empirically. That's what the authors claim in the drop edge paper. And they also can be used to generate different views of the given graph to support some tasks like the contrastive learning. And we will introduce very soon. Okay, the second artificial dynamics I want to introduce is named random augmentation. So it's a family of the augmentation techniques. And I want to use this paper as a start point of this technique. The paper name is Graph Contrastive Learning with Augmentations. So the task they are working on is unsupervised graph level representation learning. And the artificial dynamics involved is a family of random augmentation and we will introduce very soon. So the goal is to support contrastive learning on graph data. So if audience know something about contrastive learning, I think the overall framework will be very much easier for you to understand. So the overall framework of graph contrastive learning is, at first we are given graph G, and we use some heuristic-based augmentation to generate two views, right? G1 and G2. And we feed it into some GNN encoder to conduct the representation learning task and get to representation learning a represented matrix of vectors, Z1 and Z2, right? And we try to maximize the agreement between those two views, okay? And for sure, in the real world implementation, some techniques like the negative sample will be applied, but we don't introduce too much details here. So the key things is what the augmentation they use, right? I said they are a family of random augmentations. So on the image data, there are some random augmentations like randomly masking a part of the image. Right? And on the graph data, those augmentations also works. So the augmentation methods they use in this paper are the following four. The first is node dropping. So as the name says, it randomly drops a part of the node from the given graph. And the second is edge perturbation. So this includes the drop edge technique we just introduced, but it also randomly adds some links to the given graph, right? And the third one is the attribute masking, which means zeroing out a part of the node features matrix, right? And the fourth one is subgraph. So some audience might say the node dropping is equivalent to subgraph, right? The answer is yes, but the subgraph technique they're working on is guided by some node importance metric like the PageRank scores. So their key idea is to select the most important node in the given graph and drop those non-important nodes in the given graph. Okay, so we introduced 4 augmentation techniques to generate 2 views of the graph contrastive learning. And what about the performance? These authors give us such a matrix, and the x-axis and the y-axis are different combinations of the augmentations of those 2 views used in graph contrastive learning. And the red blocks means positive results compared with baselines. And the blue box means the negative results. And what I mean baseline is that this is unsupervised representation learning work, right? So the baseline is supervised settings, so which means they directly use a graph convolution networks to training from scratch, okay? And there are 2 important findings. The first is that the selection of the augmentation method is critical. And we can see over 4 data sets, almost on every data set, we can observe both this existence of red blocks and blue box, which means sometimes the performance is positive and sometimes it's negative. And even worse is that the augmentations cannot generalize across different data sets. What I mean is because some combinations can get positive results on dataset A, but if we use the exact same combination of the augmentation methods to dataset B, it might get negative performance. For example, if we select the attribute masking, both views apply the attribute masking, and it can get positive performance on proteins and the collab dataset, but it get negative performance on the NCI1 dataset and the RDTB dataset, right? So that's the kind of like the main drawback of the random augmentations. And what even worse is the hyperparameter settings also matters. For example, for the edge perturbation augmentation techniques, we have only one hyperparameter to decide how many edges to be dropped in every augmentations, right? So the authors of this paper find that on the NCI1 dataset, which is shown on the left-hand image, if we drop 10% of the edges to augment the given graph, it gets the best performance. While on the collab dataset, in order to get the best performance, we might need to drop 70%. So in other words, the hyperparameter selection is also not generalizable across different datasets. So the conclusion is that if we use a random augmentation to generate the views of the graph contrastive learning, it is labor intensive, right? So there are some related works. As we mentioned, both the selection of the augmentation combinations and the hyperparameters are critical, and the related work too try to solve the combination of the augmentations. They try to learn to select the combination of the augmentations such that it can get the optimal performance, and they put it into a meta-learning framework. And the related work 3 try to address what is the optimal hyperparameter for the augmentation methods to support the graph contrastive learning. And they try to set the hyperparameter guided by some metrics, but this is also heuristic based because those metrics are not learnable. For example, they will adapt the node dropping probability across to the node centrality to say that if the node is more important, then the node dropping probability will be low. Okay, the third work I'm going to introduce is named the supernode. So supernode is also a very simple artificial dynamics, and this is a family of work included these techniques. And we select 4 works and try to wrap them together to introduce to you, and hope we can get a general picture about what this technique is doing. So for those 4 works, the task they are working on is node and graph property prediction. And the artificial dynamics, as our bottom image shows, is insert a supernode into the given graph. Also, the supernode technique is also known as the virtual node, master node, and dummy node. So the goal are twofold. On one hand, if we insert a supernode into the given graph, it can improve the message passing of the graph neural network. That is because if the link between the supernode and the original node are bidirected, then every original node are at most 2 hops away from each other, right? So the message passing can be improved. And on the other hand, it can be used as a readout node for the graph level task. So as we mentioned in the first part, if we wanted to do some graph level tasks, the graph neural network's lastly will be some readout function to generate a graph level representation, right? But if we have a supernode connecting to all the original node, then the representation of the supernode can naturally be used as the representation of the graph itself. Okay, here is a side-to-side comparison about different methods applying the supernode trick. The difference is mainly at the edges between the supernode and the original. And on the other hand, another difference is that how could we initialize the feature of the supernode? So only related worth 3 set the link between the supernode and the original node as weighted, and they try to learn this weight by a gated function. And the related work 2 set the links between the supernode and the original node as directed. And the specific direction is from the original node to the supernode. And this is a very smart design. The reason is because they try to use the supernode to serve as the readout function. And if the link direction is from the original node to the supernode, then the insert of the supernode won't affect the message passing among the original node, right? And the third difference is that the node feature of the supernode. So work 1, 3, and 4 set the supernode node feature at a different dimension compared with the original node. So what I mean different dimensions because if they wanted to do some message passing operations like the aggregation, they will first need to map the original node feature and the supernode feature into a same feature dimension. And after that, they can do some aggregation or summation operations. Okay. And the related work 2 and work 2 and 4 use the node representation of the supernode as the readout of the whole graph. And let us see the effectiveness of the supernode. So as I said, this technique is highly flexible and applied by many works. So I select some statistics from the leaderboard of the OGB dataset, which is a popular academic research dataset. And we find a lot of work applied the technique into their works. So for example, on the OGB GMOL HIV dataset, some leading methods included the virtual node into their method like the GIN or the flag. And on the other dataset, sorry, I forgot to change the dataset name. The ranked 4th method included the virtual node into their nested GIN method. And okay, the fourth technique I'm want to introduce is topology encoding. Okay, so this topology encoding technique do not change the given topology, the topology of the given graph. And on the other hand, it will try to enhance the node features by encoding some information from the topology. And this is also a family of work, and the work we use select as the represented work is named the distance encoding. And they claim that after applying this distance encoding, the neural network will be provably more powerful than graph neural network do not equip this technique. So let us first take a look at what the task they are working on. So they claim that their work is representation learning for a targeted subgraph S. And what we mean by a targeted subgraph, actually this setting is quite flexible. So if the subgraph contains only one node, then the task is fundamentally representation learning for a node, right? So if the subgraph contains two nodes, then it generates representation for a node pair. And this task can be naturally transferred to some task like link prediction. Right? And if the target subgraph includes all the nodes in this graph, then this task is fundamentally the graph level representation learning. Right? So the artificial dynamics they apply in this paper is to generate some actual node features by encoding the topology. And more importantly, this kind of topology information is hard to be captured by a great number of graph neural networks. And to be specific, they are named as 1WL GNNs. We will introduce very soon. So the goal is clear. They will try to enrich the informative of node features to drive more powerful graph neural networks. And then the mathematic operations is as follows. So they will concatenate the raw feature of a node with some encoded topology features. And we will introduce what the DE means in this in the following slides. So we should first talk about what is the expressive limitation of 1WL graph neural networks. But before that, let's take a look at some facts. So here we have two graphs, right? And they are clearly not the same. The graph 1 and graph 2 both contain two loops, but the loops in graph 1 contain like 6 nodes, but the loop in graph 2 contains only 5 nodes, right? So they are of different structure. But we can easily find the node pairs from these two graphs such that they share the same rotated tree, right? So what I mean rotated tree is for the target node, we will put it in the first layer of the tree, and its one hope neighborhoods will put in the second layer, and its two hope neighborhoods will put at a third layer, and so on and so forth. So we can easily find node pairs from two different graphs, but they share the same rotated tree, and we can even find more examples here. So the fact is that if they share the same rotated tree, graph neural network cannot distinguish them. The reason is because both the graph neural networks and the famous Weisfeiler-Lehmann graph isomorphism test will try to generate node embeddings or node representations from the leaf node and aggregate it into the parent nodes and do a mapping to map the node feature into new representations and keep aggregate and keep update the node features and so on and so forth. So why we name those YWLGNs is because what those graph neural networks in most of the cases is not as powerful as the Weisfeiler-Lehmann test. The difference is that for the Weisfeiler-Lehmann test, they will try to hold such a multi-set like this. But for the graph neural networks, they will usually do some aggregations, like they sum them together, right? So this summation is not as powerful as the representation of the multiset. And on the other hand, the mapping function applied by graph neural networks is usually some MLP, right? The feed-forward networks, and it's not in most of cases is not as powerful as the hash functions selected by those Weisfeiler-Lehmann tests. Okay, so after we introduce background, we know that graph neural network cannot distinguish node pairs from two different graphs. And in these settings, graph 1 and graph 2 have exactly the same number of nodes, right? And we can always find the node pair share the same rotated tree from graph 1 and graph 2. So if we generate graph embedding for those graph 1 and graph 2, the final graph embedding will always be the same, right? Yeah. So given this in mind, some following up work proposed that graph neural network are not substructure aware, which is just what we mentioned. They are of different structure, but with the same graph representations by graph neural networks. And some work even propose that graph neural networks are not position aware, which means that nodes at a different position may have the same rotated tree. So those nodes at a different position of the graph can have the same node representations, and that's not ideal for some graph mining tasks. Okay, so let's talk about what the distance encoding is doing. As I mentioned, they try to concatenate some topology information into the given node features. And here the O plus operation means concatenation, and the DE means the distance encoding between two objectives. So for the distance encoding between a node U and a target subgraph S, it is the aggregation of the distance encoding between U and every node from the subgraph S. Okay. So the key problem is, how could we select the distance between two nodes? And this is actually not a very hard problem on the graph settings, right? So we can select the distance between two nodes, node U and node V, by its PageRank score. So this formula is actually generalize the PageRank score, and if we view the entries UV in the normalized adjacency matrix as the transportation probability between two node pairs, then this generalized PageRank score could be viewed as the landing probability starting from the node U to move to node V in any hopes. Okay. And there are other selections, such like the shortest path distance, which is quite straightforward, right? So after these distance encoding techniques, the authors try to do some experiments to see that if this technique indeed enhance the expressiveness of the graph neural networks. And their experiments are actually quite complicated. That is because they have 3 tasks, and for different tasks, the number of the nodes contained in the target subgraphs are different. As I mentioned, if the subgraph S only contains 1 node, and this is actually a node level task, right? If the subgraph S contains 2 nodes, then there will be a node pair level, such like the link prediction task. And if the subgraph S contains 3 nodes, then which is equivalent to the task 3 in this paper. So they will try to determine whether those 3 nodes will form a triangle or not. Okay. So another thing you need to keep in mind in these experiments, because they try to encode the topology information into the given node features, so they try to isolate the node topology information from the given node features. So in their experiments, all those data sets are non-attribute, and they try to see that if the enriched topology information can drive stronger graph neural network models, and the answer is yes. So the graph neural networks equipped with the distance encoding technique get the best performance, as the bottom of the table shows. Okay, there are some related works about distance encoding. As we mentioned at the limitation of the expressiveness of graph neural network, we know that the distance is not the only information that is hard to be captured. And we just mentioned some substructure that cannot be captured by graph neural networks. So the related work 2 and 3 try to augment the node feature by the count of various graph motifs. For example, they will try to enhance the node feature by the number of circles these nodes are involved into. And some recent work even shows that we can directly add some random features into the given node features, and it can also enhance the expressiveness of the graph neural network. The reason why they use a very naive settings where all the nodes are with identical features. So in these settings, all the nodes are the same if we do not take a look at their neighborhood, right? And they claim that after adding some random features, every node will have different identities, right? I know some random features might conflict with each other, but that's not always the case. So after adding some random features into the node features, we can distinguish which node is which and enhance the expressiveness of the graph neural networks. Okay, and there are many other heuristic artificial dynamics, such like the graph diffusion, which means that we do not directly use the normalized adjacency matrix to do the diffusion. We can do some operations. For example, we can use the generalized PageRank diffusion matrix instead, right? And we can also do some low rank approximation towards the adjacency matrix and get this low rank approximative version for the graph diffusion. And in some settings, maybe we are maybe some node features are missing, and that's not what we want for the graph neural networks. So we can recover those missing features based on for example, the feature of its neighborhood, right? We can use the pooled feature of its neighborhood to serve as the feature of this of the node whose features are missing, right? And there are many other works covered in this topic. So let's have a quick question and answering about the first part of the artificial dynamics. Any questions?
Hi, thanks for the great presentation. I'm Ling Hao from Monash University. So I have a small question about the definition of artificial dynamic. So basically, you try to permute the graph structure. So what's the difference between the artificial dynamics and the graph structure learning?
Oh, graph structure learning is a part of the artificial dynamics. So graph structure learning can be involved into technique of the graph augmentations, right? So it augments the given graph topology, and the artificial dynamics included, but also we can augment the node, the feature matrix as well. So that's the difference.
Okay, thanks. So another question is, you mentioned the dynamics, but I think that the augmentation strategy is fixed during the procedure. So why you call it dynamics?
Oh, your question is why those techniques are called artificial dynamics, right? That is because we have a dynamic from the given graph to augmented graph, and we can even augment it in many steps. Right? So that form a dynamic.
Okay, so the sub question is basically I thought the graph you mentioned is all static graph. So is that a possibility to apply this technology for temporal graph?
Good question. Good question. Actually, we will mention it in our open question sections. And follow your questions. Not only we try to we have some work, but not a lot, to augment the temporal graph neural networks. We also have some incoming work try to augment the heterogeneous information network or hypergraph settings. So they are all interesting, but also challenges.
Okay, great. Thanks for the answer.
Thank you. Okay, thank you for the question, and let's move on. So we just introduced some works about heuristic-based techniques, and let us introduce some work that are data-driven. So the augmentation methods are guided by the downstream tasks or guided by the downstream task performance. Okay. So the first work I want to introduce is named Gasoline, and this is a work from our team. So the paper name is Graph Sanitation with Application to Node Classification. So as the paper name shows, our task working on is node classification. And the artificial dynamic we are working on is to view the graph data itself as a hyperparameter. And we apply some techniques from the hyperparameter training to learn the optimal graph data. And more specifically, we form it as a bi-level optimization problem under the umbrella of meta-learning. And our goal is to improve the node classification performance. So it is very direct. Our goal is improve the node classification performance and guided by this through our paper. So the objective function is as follows. So this is a bi-level optimization problem. And let's first take a look at the lower level problem. So the lower level is a training procedure of maybe a graph neural network or any other graph mining models. And we are given a graph, and the theta is the parameter of our mining task. And we are given some training data, right? For node classification, we will given some node will be labeled, right? And after that, based on that, we can get a trained model. Here we present it as theta star. And the upper level problem is to evaluate whether this trained model can get good performance on validation set or not. And the upper level problem is fundamentally similar as the lower level problem, but we changed the node we changed the graph to evaluate this trained graph classifier. And we claim that our goal is to get the best validation performance by changing the given graph itself. And our goal is to find an optimal graph, which is labeled as tilde G. And we have another constraint to see that the modified graph tilde G should not be too away from the given graph. So we have a distance constraint, see that the distance between the modified graph and the given graph should be less or equal to the budget B, and we name it as the sanitation budget. And this formula is still a little bit abstract, so we try to instantiate into the node classification settings. So here, the lower level problem is the training objective over a training set, right? Some over the training nodes, and we select the negative log likelihood objective function. And after we obtain a trained graph neural network, theta star, we also use the negative log likelihood objective function to evaluate its performance over the validation nodes, and we try to minimize the validation loss. Okay. So as we said, our method is data-driven. So we try to solve it by some gradient-based method. And the key problem is, how could we get the gradient of the upper level problem with respect to the given graph G? And in order to get this gradient, it contains many terms actually. That is because the graph G not only involved in the final validation steps, but it also involved in the whole training steps of the given of the graph neural networks, right? So as the blue box shows, the lower level problem, we get a theta star, and the theta star actually could be viewed as a function of the given graph, right? So in order to get the gradient of the upper level problem with respect to the graph data G, it contains many terms inferred from the chain rule. So a classic solution towards this problem is view the training upper level problem, which is the training process, as a dynamic system, and which will converge in T iterations. And we unfold this process and get the hypergradient from every steps, which is shown as the dashed orange lines in our illustration figures. So this process clearly is pretty time consuming because it involves lots of the matrix multiplications between those Jacobian matrix. So we apply a famous trick named the first order approximation. So we drop those terms contains the Jacobian matrix, and we directly used the direct gradient from the upper level problem with respect to the graph data G, and use it as our gradient to update the graph data itself. Okay. So given the upper level problem's gradient with respect to the graph data G, how can we do the artificial dynamics? Our first solution is straightforward. We can directly use the gradient descent, right? But here the learning rate is constrained by the budget because we hope the modified graph should not be too far away from the given graph, right? And in some settings, we try to keep the updated adjacency matrix as discrete as possible. So we, in order to ensure that, we import a technique named the score matrix. So the score matrix is directly is exactly of the same shape as the adjacency matrix, and we will flip the entries in the adjacency matrix whose entry get the largest score in the score matrix. Okay. So let's dive into some details here. So the score matrix is the Hadamard product between two matrices, which is the preference matrix and availability matrix. And assume that in the given graph, node I and node J are connected. So their entries in the adjacency matrix are equal to 1. And we can see the availability matrix will show that its entry is -1. That is because the availability matrix is equivalent to 1 minus 2 multiplied A, right? So if Aij is 1, then the corresponding entry in the availability matrix will be -1, right? And at the same time, if the graph's our framework thinks that the negative hypergradient will be larger than 0, that means the model believe the node I and node J should be adding some links between them. But that's not good because node I and node J are already connected, so we cannot add more links between them. So finally, the score matrix will show that the corresponding ij entry will be negative, and that means this operation is not encouraged. And if our framework computes that the negative hypergradient is less than 0, then finally, in these settings, node I and J are connected, then the score matrix will show positive results, which means that deleting links between the node I and node J are encouraged. Okay. And we have some speed up method. The reason why we want to speed it up because even though the given graph adjacency matrix is sparse, its gradient matrix could be dense. And the gradient matrix complexity is usually quadratic with respect to the number of node n. So let's have a quick recap of our goal. We try to learn an incremental matrix delta A, right? And try to update the given graph. So the key idea is that this modification could be implemented over a small set of nodes. For example, we can decompose the incremental matrix into the multiplication between two low-rank matrices, U and V. And we can directly learn the decompose the matrix U and V instead of learning the modification towards the adjacency matrix. So in our problem, we initialize those two low-rank matrices as zero mean Gaussian matrix, and we almost do not change anything about our framework. We directly change the representation of the graph topology and use the same method as I just mentioned in our overall framework. So we can get the hypergradient of the upper level problem with respect to the low-rank matrix U and V respectively. And then we can update those low-rank matrix U and V in the continuous way as we did for the adjacency matrix. And in this way, if we decompose this incremental matrix, our computation complexity can be lowered, and it is linear with respect to the number of node n and the number of edge m. And in comparison, it was quadratic with respect to the number of nodes if we do not apply this tree. Here are some empirical performance. So we find that our model gasoline, here we shot it as G, performs the best over the Cora and Sci-C datasets. So the letters after the hyphen means some variance. So say we update the graph topology or update the node features in the continuous or discrete way. And we find that we didn't get the best performance over the POBLOG datasets. So we try to incorporate our proposed gasoline with some model-based methods, such like the GAT, SVD, and robust graph convolution nets. And we find that after our method is incorporated with this established method, we can still improve their performance, and the merged model can get the best performance among all the datasets. Here's efficacy study about the low-rank version. So our low-rank method is actually an approximating method, but it still can get very good performance compared with the full-rank version. And surprisingly, we can even get very strong performance on the POBLOG datasets, even better than the full-rank version. And we explain that is because the POBLOG dataset is fundamentally low-rank. So such a low-rank updating would be more suitable for these POBLOG datasets. And on the efficiency, we find that the low-rank version is much efficient compared with the full-rank version. This is what we expected from our complexity analysis. So here are some related works. We give a very general formulation about the, which is shown on the right upper corner, and we instantiate in the node classification task. But actually, this can be setting beyond the node classification. For example, we can do some ranking task, right? And the classic method to do the ranking is PageRank. but we can add some constraints into the upper level problem. For example, we can require some node pairs order, right? Because for some ranking tasks, we have some priority to say that this rank should be ranked higher than another node, right? So such constraint can be put into our gasoline framework to guide the modification of the given graph. And this task is actually being studied, and they named it as the supervised random work. And in addition, our gasoline updated the graph in a deterministic way, right? We flip it, or we do some learning rate constraint gradient descent. But we can also learn we can update the graph by updating its graph generation matrix. For example, some work like LDS formulate the graph topology as the Bernoulli matrix, whose entries represents the probability that two node pairs will be connected or not. And they try to update such a graph generation matrix instead. Okay. And let's move on to the second work, the second data-driven technique, and it's named Aerial. So the paper we presented is adversarial graph contrastive learning with information regularization. So just a quick recap, the graph contrastive learning work we just introduced before apply those heuristics-based augmentations, right? So in this paper, we try to do it automatically to learn an optimal contrastive learning way to support the graph contrastive learning. So the task, as we mentioned before, is self-supervised node classification learning, and it's unsupervised. And the artificial dynamic is used the adversarial attack to generate an actual view, okay? And our final goal, as all the other data-driven works, directly to improve the graph contrastive learning performance. Our goal is actually consistent with the task goal, right? So this is the framework of the Aerial. It's a little bit complex, but there are some common things with the graph contrastive learning work we introduced before. So given a graph G, we will also select it to heuristic-based augmentation T1 and T2 to generate two views, G1 and G2. So this part is the same as the contrastive learning work we just introduced before. And the difference lies that after we generate two views, G1 and G2, we will use the adversarial attack to attack one of the view. So in this illustration picture, we will attack the view G1, and we will have an attacked view, G adversarial. So in total, we have three views now, and we design some contrastive objectives based on these three views. So that's the overall picture of our work. And so the question is, how can we do this attack? And actually, there are a lot of graph attack works. So the graph attack works we are working on in this paper is projected gradient descent attack. So the goal is like we try to maximize the contrastive loss between the view G1 and the attacked view G adversarial. And also we have some constraint to limit the distance between the G1 and G adversarial. As we mentioned, because we do not want the attacked view to be too far away from the given graph. Okay. So instead of limit the distance between the graph G1 and the adversarial view G adversarial, we try to learn two perturbation matrix, and we try to limit the norm of those two perturbation matrix instead. So here we have two perturbation matrix. One is on the topology, and the other one is on the feature. The perturbation matrix on topology is notated LA, and the feature perturbation matrix is notated as LX. So we directly add the feature perturbation matrix into the given feature matrix as X to form the perturbated feature matrix X adversarial. And for the perturbation matrix on the topology, we design in this way is because we try to keep it as discrete as possible. So that's a common property of the graph data. We try to keep the topology sparse and discrete. So we do the perturbation over a matrix which is highlighted in the parentheses and a Hadamard product with the topology perturbation matrix. So ideally, this topology perturbation matrix should be binary. As I said, we will try to keep it discrete, but that's hard for us to do the optimization, right? Because that will lead to some combination problem. So we relax this topology perturbation matrix into the continuous domain, which is within the range of 0 and 1. And after that, we finish the optimization. We can return it to a discrete matrix by sampling or by setting a threshold, right? So let's take a look at some details about the project gradient descent attack. This is an established attack, both on image data and on our graph data. So the core idea of the PGD attack is, first we do some gradient ascent, and then we get the modified data, and then we try to project it back to an ideal area because we have some constraints over the variable. We try, in our settings, we have a constraint on the distance between the perturbated graph and the given graph, right? So the formula is as follows, and there are two things you need to pay attention. The first is that the operation is a plus instead of a minus. So the minus, it means gradient descent, right? But in our settings, because the objective function is somehow like an attack loss, so usually the setting of the attack loss will be the negative of the functionality loss, right? So for the attack settings, we try to maximize the utility loss, right? So this is why we set a plus here. And the second thing is that the gradient ascent is wrapped with a projection operator pi. So the pi means that we try to limit the updated perturbation matrix into an area, and this area is actually bounded by its norm. Okay. So here, this is the some details about why we bounded the perturbation of the topology and the feature matrix. So we won't dive into too much details here, but the normalization bound of norm bound of the feature matrix, we select the maximum bound. So to see that the maximum change over the feature will not be larger or will not be larger than the delta x. And for the norm bound of this adjacency matrix, we bound its sum of the entries from the topology perturbation matrix to be less or equal to the delta A. So for the reason why I select those two bounds to bound the feature perturbation and topology perturbation, please check our paper instead. So after that, we are given this PGD formula, and we do the gradient ascent. We will try to design this projection function, right? So for the projection over the feature topology matrix Lx, we directly clip it into the range minus delta x and positive delta x. That is because our bound is over the maximum norm, right? And for the topology, for the projection on the topology perturbation, the formula is a little bit complex, but let's take a look at its core idea. Its core idea is try to find that mu, which exactly move the topology perturbation matrix into the boundary of the ideal area of SA. Okay. And another novelty of this work is that it sets some regularization over the heuristic-based generated view, T1 and T2. G1 and G2. So why we have such a regularization term is because we do not expect the view generated by the heuristic method to be too similar. Why? It's because if those two views, G1 and G2, are very similar, then our downstream contrastive learning module cannot run anything, right? Because they are already similar. It's very easy to get the maximize the agreement between those two views. So that's not what we want. So we try to let the generated view G1 and G2 not too similar with each other. And how to measure that they are not too similar, our core idea is that the similarity between the two views G1 and G2 should be less than the similarity between the given graph G and any of its augmented view. So in other words, if we measure the similarity between G1 and G2 as the L12, and the similarity between the given graph and the one-off view as the L1 and L2, we believe that the L12 should be larger or equal than the similarity L1 or L2. Okay, so that's the core idea. We try to penalize those trivial augmentations such that those two generated views are similar with each other. Okay. So here is the final objective function. So the objective function contains 3 terms. The first term is the classic contrastive learning loss between two views generated by the heuristic-based augmentation G1 and G2. And another adversarial contrastive learning loss is between one of the heuristic-based augmented view G1 and the data-driven view G adversarial. And also, the third term is the regularization term we just mentioned to penalize those trivial heuristic-based augmented view. And here are some empirical performance of Aerial, and we find that it gets the best performance compared with no matter the supervised method or the contrastive learning-based baseline method. And because we involve an adversarial attack into our framework, so this idea is actually shares some similarity as the method named adversarial training, which is a defense method. So the Aerial shows some robustness against the attack over the given graph. So under the attack, under the poisoned attack settings, the Aerial get the best performance compared with all the baseline methods. And there are some related works. The first related works, as I mentioned, is graph virtual adversarial training. And also there are some works on the graph level representations adopt this adversarial graph augmentation technique into the view generation for the graph contrastive learning. That's the related work 3. But difference is that they are working on the graph level task, and this work is working on the node level task. And the third point is that there are some work to drive there's some work which are data driven, and they are working on the augmentation of the hypergraph, as our audience mentioned. So this is beyond the scope of the plain statistic graph. Okay, and the last data-driven technique I want to introduce is named GNN. So the paper name is graph condensation for graph neural networks, and the task they are working on is for node classification. And the artificial dynamics they are working on is try to synthesize a smaller graph. And at the same time, if a graph neural network trained over this smaller graph can get comparable performance over another graph neural network trained on a large graph. And the goal is clearly, if we have an informative small graph for the training of graph neural network, then we can save some storage space, and the training time will be saved a lot, right? So let's take a look at the objective function. So given a large graph, we here noted its adjacency matrix, feature matrix, and node features A, X, Y, respectively. And the large graph is noted as T. And our goal is to find an optimized synthetic graph S, which is much smaller compared with the given graph T. So this is the objective function. And the core idea is that they try to merge the training trajectory over S and T respectively. The reason is because if those the training trajectory over S and T are exactly the same, then under the same initialization, the converged graph neural network will be the same as well, right? So they try to match the training trajectory on T and S on every step. So that's the reason why they have a summation over the training steps. And also, as I mentioned, they try to ensure under every graph neural network initializations, the training trajectory can always be matched. So they have an expectation over the rectangle parenthesis. That's the first shoes. And here, a key hyperparameter is the distance function. So how to measure the distance between two changing trajectories? This is kind of flexible. And the paper GNN select the sum of the cosine distance of every layer of the graph neural networks. So in order to solve this objective function in a gradient descent way and get the final converged synthetic graph S, they apply some tricks. The first trick they use is mini-batch. And the reason is because if we directly feed a large graph T into the graph neural network, then we will face the out-of-memory problem. So in practice, in every updating steps, they will sample the T into a T sub S, and to match the training trajectory of T on T sub S and the training trajectory on the S. And in the other training steps, they will resample to ensure the information of the T all be captured. And another problem is because it is to save the space of the adjacency matrix. So we know that the adjacency matrix is m by m matrix, right? So the search space is quadratic with respect to the number of nodes, and that will somehow be heavy. So the authors of this paper claim that we can encode the adjacency matrix by the encoding of the feature matrix. So they claim that if we already learn the optimal feature matrix, then we can infer the optimal adjacency matrix from the given node feature, from the learned node features. So their specific formula is as follows. So they feed the node feature I, they feed the node feature I and node feature J into MLP, and then wrap it with a sigmoid function to learn the adjacency matrix between node I and node J fall into the range between 0 and 1. Okay. They also propose a graphless version, and this is like a variant of the full version GNN. So instead of learning both the adjacency matrix and the node feature matrix, they claim that we might directly set the learned adjacency matrix as I, which is the identical matrix. So in other words, they claim that maybe we do not need to learn this topology. We can just learn, we can directly learn tabular data. So the core idea is that they try to converge a large graph data into a small tabular data. And this setting is interesting because what they fundamentally doing is the representation learning work too, right? But this representation learning work is special because they do not learn a representation of every node. They only learn the representation of a small number of synthetic nodes. Okay. So here the empirical performance. So the authors of GNN find that in terms of the graph condensation task, the GNN can get the state-of-the-art performance compared with some baselines. So at the time this paper is published, the previous work tried to shrink the size of the graph data set heuristic based. So they usually set those central nodes, or they select some important nodes from the given graph to shrink the size of the given training graph. And they find that this data-driven method get the best performance. And even the structure-free version, which I mentioned, directly learn tabular data from the large graph data, can still get very good performance compared with all the baselines. And the paper, also of this paper, also find that the GNN shows broader applicability. So in their experiments, they find that this learned small graph can drive the training of a broader range of graph neural networks. So in this table, they find that this learned graph can also support the graph neural network like GAT, APP, MT, graph SAGE, and SGC, and even can support the training of a simple MLP over the given graph. Okay, here are all the content about the data-driven techniques for artificial dynamics. Any questions? If no, then we're gonna move forward. Okay, let's move to the last part of this tutorial, the open questions and challenges. The first question is, we mentioned a lot about how to augment the graph topology and the graph features. So how could we augment their temporal features? A direct answer is we can randomly add some noise to these temporal features, right? As a lot of the heuristic-based method did on the topology and the feature component. And this is there's a work published I forgot, it should be on NURBS, apply these ideas, and their temporal graph neural network applied is follow the recurrent unit design. So here they will try to update the backbone model they select is try to update every node's status by such a recurrent update function, and they try to order every edge in a link or in a time order and feed the feature edge feature and the connected node feature one by one into the recurrent union to update their node feature. So they try to use random augmentations to augment these temporal graph neural networks. And the task they are working on is edge perturbation and node classification. And as I mentioned, they apply the heuristic-based artificial dynamics to randomly perturbate the time property of the graph components. And their goal is that they can improve the temporal graph neural network's performance. So their core idea is that they not only augmenting the topology features, topology information of the given graph, but they also augment the time features. And their idea is to generate a set of augmented temporal graphs and merge them together to boost the temporal graph, to boost the task performance over the temporal graphs. So let's take an example to see how their method works. They will augment the given temporal graphs by different augmentation amplitude. What I mean by augmentation amplitude is like on one graph we may drop 10% of the edges, and on the other graph we can drop 80% of the edges. So in this demo example, we only generate two views of the given temporal graphs, and the one is dropped 10%, and the other one is dropping 80% of the edges. And what their idea doing is try to modify something from this recurrent union equation. So they still update the node representations from the less random view, which is the view that dropping 10% of edge in our demo example. But they try to merge the information. They try to merge the node embedding from the more random view. So here, the Sj super mean function over the L plus 1 and the capital L means that they try to merge the information from the view that is more random than the base view. So in this demo example, they try to merge the information from the view that dropping 80% of the edges into the view that dropping 10% of the edges. And after that, they will use the node embeddings from the less random view as the final node embedding of the given node to support the tasks over the temporal graph as the existing works on temporal graph did. And they find that their methods are flexible because they only change the flow of the recurrent union aggregation. So their method can be applied to a series of the temporal graph models. The only difference is how to design the recurrent union for this family of works. So they find that their proposed work method can enhance two models, which is dy rep and TGN, which are two recurrent union temporal graph neural networks. And after equipped those two works with the meta proposed by this paper, they get the best performance compared with the other baselines. And also, they can also work on the edge level task and node level task, as many recurrent graph neural network did. But for brevity, we only show the performance over the edge level task in this tutorial. And the open question 2 is how to augment the temporal graph in a data-driven way. So this is very critical, and we have witnessed a lot of success of the data-driven method compared with the heuristic-based method. But how to augment the temporal graph in a data-driven way? And from our last work, the time feature is only used to sort the edge in order, right? As I show you here. So the time property is not explicitly included into the computation of the final objective function. They only use the time property to sort the edges, right? So if the time property is not clearly involved into the final objective function, then how can we compute something like the gradient of the objective function with respect to the time property t, right? If we cannot compute such gradient, how can we update the perturbation t in a data-driven way? This is totally unknown so far. And the third question is, given temporal graph, for the discrete cases, it can be viewed as a sequence of static graph snapshots, right? So if we doing the data-driven augmentation on every view separately, then the computation cost will be linear with respect to the number of the graph snapshots, right? So that will be really time-consuming. And there are some smoothness constraints among different graph snapshots, right? So if there also exists some smoothness constraint between the augmented graph snapshots in a smoothness way, right? So if such a smoothness constraint exists, then maybe we can only augment the first graph snapshots and incrementally get the optimal augmented graph snapshots in the following time steps, right? But clearly, no work so far on this topic. And the last open question is how to generate new graph snapshots given the previous observed one. So in the first part, Dongqi mentioned there are some works try to generate the new graph snapshots, but they are not served for the final downstream tasks. So this question is actually highly open because we are totally unknown how many graphs to be generated, right? So we can generate 10 graphs or 20 graphs. So how to select the number of generated graphs to ensure that our final task performance is improved, right? And also, we also have no idea what is the size of the generated graphs, right? Maybe we can increase the size of the generated graph in the following steps, or maybe we should shrink the size of the generated graphs. And this search is actually non-differentiable in my view. So we have no idea how to generate a new graph snapshot to serve for the final downstream tasks. Okay, there are some resources. The first two surveys are from our teams, and the third survey is from guys from the Notre Dame. And there are some related tutorials about the representation learning of graph neural networks and the few shot or the data efficient learning or the temporal graphs. Okay. Okay, any questions?